Hello, I'm Maria, and this is a quick guided look at this poster titled Frequency Fluctuations and Stability of Power Grids with a Large Renewable Penetration Ratio. So what we propose in this poster is a dynamical model to study power grid stability in scenarios of high renewable penetration, and in particular, we present the case of Gran Canaria. So as you may know, in the power grid there are two sides, the demand and the generation, and they must be balanced at all times to ensure grid stability. And a good indicator of that balance is the grid frequency. So what happens is that, for instance, if the demand increases, the frequency will decrease, and we will have to increase the generation in order to match the demand and restore the frequency back to its nominal value. And doing this with conventional generation is not much of a problem, but when we have a high share of renewable generation, then we have to overcome three main challenges. And these are the fact that renewable generation sources are unpredictable, and then as renewable generation substitutes conventional generation, we will have less conventional control capacity, and finally the fact that renewable generation does not provide rotational inertia, which traditionally plays an important role in frequency control. So we model the power grid as a network of interacting nodes, and we will have two types of nodes. First, conventional generation nodes, which we describe with these four equations. So we have an equation for the phase, an equation for the frequency, and this is the famous swing equation that describes the frequency dynamics in terms of the power balance. And this h here is the inertia constant, so this equation models the inertial response of the plant. And then we have primary and secondary control, and these are control responses that change the power output of the generator when the frequency deviates from its nominal value. And in the secondary control, we have a parameter kappa, which determines the amount of secondary control in the system. And we also have an additional term that allows us to force the power plant to a particular reference power. Then we have consumer nodes, and the thing with consumers is that they have very low inertia compared to the power plants, so they adapt immediately to the grid frequency, and so we can perform an adiabatic elimination to this frequency equation, and we obtain this other equation. And finally, for renewable generation, we simply model it as a negative load in some specific nodes of the grid. Now, one of the most interesting features of our model is the fact that we use real data. So we have 10-minute total demand and generation data. So we distribute the demand according to population of each node, and we add some correlated noise to model the fast variations. And for the generation, we distribute it by technology in each generating node. So these are the values that we will use as the reference power to force the power plants in a dispatch-like manner. So with this in mind, we took the model and we applied it to the case of Gran Canaria. And these are some of the results that we obtained. So first, we show the frequency time series, and we can see that the model captures the frequency peaks that are associated with renewable generation variations. And in general, we also see that the model reproduces the statistics of real data. So the next step in our study was to increase the amount of renewable generation in the system. So this is what we have here. We plot the rank distribution of frequency fluctuations for different amounts of installed wind power. So this is for the current installed wind power, and the other two are future scenarios where we would have 2 and 4 times the current installed wind power. So what we see is both in winter and summer that as we increase the installed wind power, frequency fluctuations also increase. And in fact, they increase so much that they threaten grid stability. So we have to increase the control capacity of the system in order to reduce these fluctuations. And this is what our next plot is about. In the left, we see that as the amount of wind increases, so does the amount of control needed to keep frequency fluctuations within some reasonable limits. And in the right, we actually have the same, but now in the horizontal axis, we have the ratio of installed wind power over total current installed power, with emphasis on the current, which is why it goes over 1. And in this case, there is a plateau that comes from the fact that as we increase the amount of wind in the system, there will be times with excess wind generation, but when this happens, we only pour into the grid the demanded amount. So doing this adds another layer of control, which is why we don't need to keep increasing secondary control as much. So that was all. Thank you for watching.